Hello there. In this lesson, we continue our investigation of the geometric representation of a complex number. In particular, in this lesson, we will learn how to use the modulus argument, also known as polar form of complex numbers. The modulus argument form of the complex number provides us an alternate method of representation of complex numbers through polar coordinates. The modulus and the argument, which we'll get into later, of complex numbers resembles their magnitude and direction, similar to in vectors. Hence, the topics of vectors and complex numbers go hand in hand in this case, and we can incorporate our understanding of vectors and vector analysis into our understanding of complex numbers, and vice versa. However, you do not have to have studied vectors to understand the content of this lesson. Therefore, the applications of the Arg form are widespread across the various applicable fields of vectors and complex numbers. These include mathematics, physics, chemistry, finance and economics, medicine, engineering, and more. In this lesson, we continue our geometric understanding of complex numbers. In particular, we define and use their modulus and argument to derive the polar form. The difficulty rating for this lesson is 5 out of 10. Our first subpoint will be to define and calculate the modulus of a complex number. Remember that we define the Cartesian form of a complex number as z equals a plus ib, where a and b are the real and imaginary components. Then recall that in the last lesson we focused on plotting this complex number as a point on the argand plane. And recall that the corresponding point to z equals a plus ib was a, b. Now we want to calculate the modulus of the complex number. This is the distance which it lies from the origin. In other words, the modulus is just like calculating the magnitude of a position vector. To do so, we will need to recall the distance formula. You will remember this from younger years, where we had d equals the square root of x2 minus x1 squared plus y2 minus y1 squared. Since the modulus is the distance of a complex number from the origin, we will use this formula to calculate it. You will recognize that if we drew a line across the x-axis to the x-coordinate and labeled it with a distance of a, and then we drew another line to the y-coordinate and labeled it with a distance of b, we produce a right-angled triangle. The hypotenuse of this triangle is the distance or the modulus of the complex number. This was how we derived the distance formula. Now using the distance formula, we will get d, but as we've got it here, the modulus of z is equal to the square root of a minus 0 squared plus b minus 0 squared, or just more simply, square root of a squared plus b squared. This is the general form for the modulus of the complex number z equals a plus ib. Now let's have a go at doing this question from the 2020 HSC. We've got the complex number w equals minus 1 plus 4i, and we want to evaluate the modulus of w. Using this formula, we will get the modulus of w is equal to the square root of minus 1 squared plus 4 squared, and that will equal the square root of 1 plus 16, which is equal to the square root of 17. Our second subpoint is to define and calculate the argument of a non-zero complex number z equals a plus ib. The argument of a complex number is the angle which it makes with the positive x-axis, that is, this axis here. By convention, we measure it in radians. Remember that pi radians is equal to 180 degrees. Now, if we've got that same complex number, z equals a plus ib, we can plot the point AB, where the x value is a and the y value is b. Now, if we want to get the angle between the complex number and the positive x-axis, that would be this angle here. We can use our understanding of trigonometry to calculate the argument, whereby tan theta would be b over a, remember, opposite over adjacent, therefore theta would be arctan of b on a. Let's have a go at this question from the 2018 HSC. So to start off, we've got the complex numbers u, v, and w. We've got u equals 5 plus 2i. Now we want to find w? Well, w is a 90-degree clockwise rotation of u, and remember we said that multiplication by I produces such an effect. Therefore, we will have w equals iu, which is equal to I 5 plus 2i, which is equal to negative 2 plus 5i. And now we need to find v. Well, v would be the addition of u plus w. This would be 5 plus 2i plus minus 2 plus 5i, which would equal 3 plus 7i. Now finally, we will use our newfound knowledge of the argument to calculate the argument of w over v. Well, first let's do w divided by v. This would be minus 2 plus 5i over 3 plus 7i, and recall that we would realize the denominator. In the end, w over v is 1 over 2 plus 1 over 2i, and to calculate the argument of w over v, this would be arctan of 1 over 2 divided by 1 over 2, which would be pi on 4. Now let's look at this question from the 2017 HSC. To calculate the argument of z, we will do arctan of root 3 over 1, which would be pi on 3. But the imaginary value is negative. So if we visualize the argand plane, in order to have a negative imaginary value but a positive real value, the complex number would have to lie in this quadrant here. Therefore, we would have the argument negative pi on 3. In other words, the complex number 1 minus root 3i would be somewhere around here. For part 2, we want to calculate the argument of z over w. Well, we could evaluate z over w first, just like we did previously, but let's use an identity. There is an identity which states the argument of a on b would be the argument of a minus the argument of b. So we will have the argument of z minus the argument of w. The argument of z, we know, is negative pi on 3, and the argument of w, we can see, would be arctan of 1, which is pi on 4. Therefore, the argument of z over w would be minus pi on 3 minus pi on 4, which is negative 7 pi on 12. The third subpoint is to define, calculate, and use the principal argument of z of a non-zero complex number as the unique value of the argument in the interval negative pi exclusive to pi inclusive. Well, the argument of a complex number is cyclical by every 2 pi radians. This makes sense because if we visualize the argand plane, a rotation by 2 pi or 360 degrees will get you right back to where you started from. For instance, if we had the argument of pi, it would be equal to the argument of negative pi, with both lying on the negative x-axis. Inversely, it means that any complex number has an infinite number of arguments, each in the form n plus or minus 2m pi, where n is what is known as the principal argument and m is an integer. As defined in the syllabus, the principal argument is the unique value of the argument from the interval negative pi exclusive to pi inclusive. What this means is, if something had an argument of, say, 2 pi, while this is still correct, it is not in this interval of the principal argument. So we would say that the principal argument would be 0. And we can do this for all arguments outside the domain. Simply, this means that in an exam, you would be expected to provide the argument of a complex number in its principal domain, between negative pi and pi. Now that we have defined both the modulus and the argument of a complex number, we can bring these two together to form the modulus argument or polar form of the complex number. This form makes the process of multiplying and dividing complex numbers more easy, and this opens up the topic to harder but more interesting arithmetic operations. The Arg form is similar to the Cartesian form. In the Cartesian form, we had z equals a plus ib, and we had the real component of z was equal to a, and the imaginary component of z was equal to b. Well, the modulus argument form is very similar in that we have a real component, and this would be r cos theta, where r is the modulus and theta is the argument, and the imaginary term is r sine theta. And just like we added the real and the imaginary terms in the Cartesian form, we will do the same with the polar form to get z equals r cos theta plus I r sine theta. And the r's can be factored out to get cos theta plus I sine theta. And this is just abbreviated to r cis theta. This is the polar or mod-arg form of a complex number. So to convert from the Cartesian form to the mod-arg form, we will first need to calculate the modulus of z and then the argument of z and put it into this form. To convert from the mod-arg form to the Cartesian form, we will evaluate the r cos theta term, and that will give us the real component, and then we will need to evaluate the r sine theta term, and that will give us the imaginary component. Now let's have a go at a few questions. So we need to first express z plus w in the modulus argument form. Well, z plus w is equal to minus 2 minus 2i plus 3 plus I, which is equal to 1 minus I. Recall, we need to get the modulus of z plus w, which is equal to the square root of 1 squared plus minus 1 squared, which is equal to root 2. And then the argument of z plus w is equal to arctan of 1 on 1, but it is in the fourth quadrant, so the argument would be minus pi on 4. Therefore, the mod-arg form of z plus w is root 2 cis minus pi on 4. Another question, this time from the 2016 HSC. I want you to pause now and then come back to see if your answer is correct. Did you get the same solution as me? If so, we'll move on. If not, pause and have a look at my solution. Now we are converting from the polar form to the Cartesian. So we have z is equal to 5 cos of 3 pi on 4 plus 5 sine of 3 pi on 4i. And we will just evaluate these, and this will give us 5 times negative 1 on root 2 plus 5 times 1 on root 2, which is equal to negative 5 on root 2 plus 5 on root 2i. Now we can rationalize the denominator to get negative 5 root 2 on 2 plus 5 root 2 on 2i. Now, in this question, we have it slightly different. We have been given a graphical version of the complex number, and we need to discern what its polar form is. We do not have anything to signify the modulus, but we can determine roughly what its argument is. Well, it is in the third quadrant, so therefore we know its argument is between negative pi on 2 and negative pi. Therefore, it cannot be A and it cannot be C, or B, that is cis of negative 2 pi on 3, but D is not in the cis form. It can be rewritten as cos of negative 2 pi on 3 plus I sine of 2 pi on 3, due to sine being an odd function. And this is definitely not the solution, so therefore it has to be B. To recap over this lesson, we have been able to define the modulus and the argument, in particular the principal argument of a complex number. This has allowed us to derive the modulus argument, also known as the polar form, and it will open us up to a variety of new operations to do with the complex numbers. Thank you for watching this lesson, and I'll see you next time.